This is our next lesson on conic sections, and in this lesson we're going to be talking about parabolas. So you can see that I've already drawn two parabolas for us here, and you'll notice that one of them opens upward, and we're kind of familiar with parabolas that look like this, but the other one opens sideways. So what we're going to do in this lesson is we're really going to shift our focus from thinking about parabolas in terms of functions, quadratic functions, and instead think about them in a geometric sense. And so the definition that we're going to give for parabolas is going to feel a lot like the definition that we gave for a circle. So I actually wrote the definition already, and I'm just going to insert it here. All right, so here it is. A parabola consists of all the points that are equidistant to a point F, called the focus, and a line called the directrix. So there's a lot to talk about here. So first of all, let's look at the example on the left, and let's plot approximately its focus and its directrix. So these are parabolas that I totally made them up. So I did not design them to have a specific focus or a specific directrix. So we're going to approximate both of them. So the focus is about here. So we'll call this point F. And then the directrix. So depending on whether the parabola opens upward or sideways, the directrix is going to be a horizontal or a vertical line. So for our purposes, since we're starting with the parabola that opens up first, the directrix is a horizontal line. In the next example, we'll look at a directrix that's vertical because the parabola opens sideways. So the definition of a parabola is that if you take any point, so let's just say here is a point xy, and you draw the line connecting that point to the focus, and the line connecting that point to the directrix, those two lines are the same length. So this is true of any point on the parabola. So I'm not going to do too many more, but if I were to pick some other point, you can see, and again, this is approximate, so it's not designed to be totally perfect, but you can see that the distance from that point to the focus is believably the same distance as the distance from that point to the directrix. Now, let's say that the directrix is the horizontal line y equals p. And in this case, because the directrix is below the x-axis, let's just make it easy on ourselves and say that y is equal to negative p. Well then, what is the distance from the point xy to the line y equals negative p? So this distance here, and you'll notice this is part of the reason why we look at parabolas that open vertically upward as opposed to looking at weird ones that open sideways. Because the line is horizontal, it's easy to determine the distance from a point. It's just the length of this vertical line. So the length of the vertical line that would just go to the x-axis would be y, and then we have to go p units more, so that's y plus p. Okay, so y plus p is the distance from this point xy down to the directrix. Now let's think about the distance to the focus, okay? So the focus, if the coordinates of the directrix are y equals negative p, then the focus is the point 0, p. And if you look at the length from the point xy to the focus, you can see that just like with the circle example, you can draw a right triangle. So the right triangle that we will draw will look like this. So a line like so, and a line like so. Okay? And you can see that the length of the blue is just x, and the length of the green is y minus p. So you can look to our lesson about circles to understand why that is. And my picture is getting a little bit busy here. But we have y minus p is the length of this blue line. Excuse me, the green line. Well, by the Pythagorean theorem, the distance, the length of the red line is x squared plus y minus p squared, right? That is the square of the length of the red line, so its square root is the length of the red line. But we know that the two red lines have the same length, so that means that that is the same as y plus p. So let's open this up, right? Meaning, let's get this into a slightly neater form. So I'm going to square both sides, and I have x squared plus y squared minus 2yp plus p squared is equal to y squared plus 2yp plus p squared. So again, to get from the first line to the second line, I squared both sides. Now check it out. I have y squared and p squared on both sides, so they just subtract off. Okay? And what I'm left with is x squared is equal to 4yp. Okay? So in other words, I could write it as y is equal to x squared over 4p. So if you have the equation of the parabola, you can also see what the focus and the directrix is. We'll come back to that in a minute. Now, let's look at this picture here. So it's exactly the same idea, except the parabola opens sideways rather than opening up. So again, we're presuming that the vertex is the origin. And I didn't mention this yet, but in a future video, maybe 3 videos from now, we'll talk about parabolas where the vertex is not the origin. We will still focus on parabolas that either open up or open sideways, but we will look at a few examples where the vertex is not the origin. So same idea, right? We know that since this is a parabola, every single point on this parabola, so no matter what point I pick on this parabola, there is a single point called the focus and a single line called the directrix, such that the distance between the point on the parabola and the focus is the same as the distance from the point on the parabola to the directrix. So I'm going to approximate them again. This is a made-up parabola, so we'll sort of eyeball it. The focus looks to be about here. So this is the focus. We'll call this F. And then the directrix, I think, is about here. So you see that when the parabola opens sideways, the directrix is a vertical line. Okay, so when, I should say, the axis of symmetry of the parabola is a horizontal line, the directrix is vertical. So, like we just said, if I pick any point on the parabola, let's just call it xy, and I look at its distance to the focus and its distance to the directrix, they are equal. So I'm not going to do too many because, as you saw in the previous example, the picture gets claustrophobic very quickly. But here is what we're saying. We're saying that if we look at the distance from the point to the focus and the distance from the point to the directrix, they are the same. And again, like I said, I eyeballed the focus and the directrix, but it's believable, right? This distance looks to be about the same as this distance. This distance looks to be about the same as this one. Well, a lot of the same symmetries are true for a parabola that opens sideways, just like they were for a parabola that opens to the vertical direction. So if the focus is this point, you see it's a point on the x-axis. Let's just say, for the sake of argument, that its coordinates are p, 0. Then the directrix is the vertical line x equals -p. Okay, so much the same way that we derived the equation of the parabola that opened up, let's derive the equation of the parabola that opens sideways. So remember, the two distances are the same. So let's start with the distance that's a little bit easier, which is the distance from the point to the directrix. Since the directrix is vertical, all I need to look at to get the distance from the point to the directrix is just, well, what's the horizontal distance I'm traveling? Since the x-coordinate of this point is x, this is x, and since the equation of the directrix is x equals -p, that second segment is p, so the distance from the point to the directrix is x plus p. So again, this should feel very, very similar to the example that we just did on the left. And you see that the distance from the point to the directrix there was y plus p. Okay, so very, very similar mechanics. Just like in the previous example, when we were talking about the distance from the point to the focus, we constructed a right triangle. We're going to do much the same thing here. So we'll do the vertical length in green. We'll do the horizontal length in blue. Now, we've done this with circles, and we've done it once with parabolas. So maybe stop my video and try to figure out what's the length of the green line and what's the length of the blue line. Okay, well, the green line in this case is a vertical line that goes from the point xy down to the x-axis. So that means that when we're talking about the distance, or I should say the length of the green line, we're simply talking about the y-coordinate of that point. So the length of the green line is simply y. Now let's talk about the blue line. So you'll notice that there are kind of two things at play here. The distance from the focus to the origin is p, okay? Because the coordinates of the focus are p, 0. So this whole distance is p. But if you look at this little distance, the one that goes from kind of our point xy to the origin, that distance is x. And the blue distance is the difference between the two. So again, this longer distance is p, this shorter distance is x. So the blue distance is p minus x. The Pythagorean Theorem comes in to save the day. The Pythagorean Theorem tells us, well, you've got yourself a right triangle here. So that means that the sum of the squares of these two sides is the square of this side. So the red length squared is p minus x squared plus y squared. But I don't want the red length squared. I want the red length. So that's the square root. So again, I really want you to sort of be noticing how similar mechanically, structurally, these two processes are. And we already know that because these two red lengths are the same, that square root of p minus x squared plus y squared is the same thing as x plus p. Well, I'm sure that you all know where this is going. You could even pause the video and work it out for yourselves. Okay, well, now that we're back, let's square both sides. So we get p minus x squared plus y squared is equal to x plus p squared. Okay, well, if you square p minus x, you'll have p squared minus 2px plus x squared is equal to y squared. And then on the right-hand side, you have x squared plus 2px plus p squared. Oh, well, this is an awful lot like what we had over there. Again, we notice that we have x squared and p squared on both sides, so they just subtract off. Okay. And now I have negative 2px and 2px on the two sides, so I'll combine them. I'll add 2px to both sides, and I end up with y squared is equal to 4px. So in the instance where you have a parabola that opens sideways, you can write its equation either as y squared is equal to 4px, or if it's more comfortable, and I think this may be more what you see in textbooks, although it'll depend on the resource, x is equal to y squared over 4p. So from here we see, and again, these are things that we'll talk about in a video on examples later, that if I'm given the equation of a parabola, I can figure out its focus and its directrix. And if I'm given the directrix or the focus of a parabola, I can figure out its equation. So we are seeing this intimate relationship between the equation of a parabola and the location of its focus and its directrix. So something to noodle on for later, and we'll mention it, not too much, but we'll mention it briefly later on. What if the vertex isn't the origin? When the vertex is the origin, you gain all of this symmetry, that the focus is p units above at 0p, and the directrix is p units below, y equals negative p. What does that look like when the origin isn't the vertex anymore? You'll notice the symmetry is still there, but the coordinates aren't quite as pretty. So that's all for a later video where we talk about what are called shifted conics, but this is the basics of parabolas.